My name's Addison Highman. I'm the chief architect here at StreamNative. I've been part of the Pulsar community for about 2.5 years, and I work a lot within the customers and the community to help with adoption of Pulsar. And happy to be able to spend some time with you here today. As mentioned, so we're going to talk about Pulsar. We're going to talk about StreamNative, who we are. We're going to discuss about why Pulsar exists, some of the idea of how the needs of modern data and streaming data. Then we're going to talk about Pulsar, its design, and the key components of Pulsar. We'll dig into that into the cluster, and then we'll dig into the code with some ideas of what it looks like to get started with sending and receiving messages to Pulsar. And then finally, we'll dig more into a little bit deeper into Pulsar's architecture and the ecosystem. And so once again, this is really about providing an overview of Pulsar as well as the community, about use cases, and we're going to cover as well additional places you can get resources to be engaged and continue learning about Pulsar. So yeah, first we'll talk a little bit about Apache Pulsar, what it is and where it comes from. So at a high level, we call Pulsar a cloud native messaging and event streaming platform. So by cloud native, it's a piece of software that's designed to really leverage the modern scale out cloud ability to add new capacity quickly, to scale back down, and to also integrate with technologies like Kubernetes that really help leverage that. And it's a messaging and event streaming platform. So meaning traditional application messaging, things like work queues, pub sub, fan out, as well as high throughput ordered streaming applications. So this is large amounts of messages that are distributed across many different instances that Pulsar can do both of those things in sort of one package. And as a bit of history, so Pulsar was initially developed inside Yahoo as their cloud messaging service. And in 2016, that was committed to open source, and in 2018 became an Apache top level project. Since then, from 2019, where StreamNative was founded, and continuing on now through 2020 and 2021, there's been a lot of adoption that's happened in very different segments. We'll talk some more about that, as well as a large growth in contributors, as well as things like additional ecosystem, like systems like KOP, AOP, these systems that allow for Pulsar to speak other protocols like Kafka or AMQP. There's lots of ways to measure growth, but some of the ones that we really like to point out and look at here is growth of contributors. So since becoming a top level project, the contributor growth, I actually think we just hit our 400th contributor in the last few days. Lots of growth in stars, as well as lots and lots of Docker image downloads, which by all estimates is from a lot of Kubernetes clusters and users. So why are they adopting Pulsar? Why is this growth happening? And really it kind of comes from, once again, these two main things that Pulsar can do uniquely, is able to do both quite well, of traditional message queuing messaging systems. So systems like ActiveMQ, SQS, RabbitMQ, more enterprise offerings like IBM MQ or TIBCO, that are adopting Pulsar because it can do scale out, high throughput messaging while still providing all those same capabilities from more powerful messaging capabilities like RabbitMQ, et cetera, as well as these data streaming technologies, things like Kafka Kinesis, where once again, we have ordered throughput or ordered requirements and high throughput and delivery guarantees of being able to replay and persist messages for periods of time. And so once again, Pulsar is unique in being able to do both of those in one system, and can really, many organizations are adopting it for its ability to simplify their architecture and simplify the deployments that they have of one system that can replace multiple systems. This is a quote from Sundar, who is the CPO of Splunk. Splunk is a large user of Pulsar. And here he mentions that they've shifted to Pulsar as their underlying streaming engine. It's their bet on long-term architecture for enterprise-grade multi-tenant streaming. So you can imagine an organization like Splunk, they're moving lots of data around, and Pulsar is key in some of the new offerings that Splunk is working on to be able to deliver really deep analysis into data, log data, and other metric data of systems. And some more reasons there. So Splunk in Pulsar Summit 2020 gave a really in-depth talk, talked about also all these reasons why that is. But from a high level, it's really about this lowering of CapEx cost, better latency improvements, as well as lower OpEx due to the layered architecture. Once again, they're processing billions of messages a day. And the presentation given at Pulsar Summit 2020 really digs into all the different, lots of different reasons for that. But they're not, the only adopter. So Iterable is another company that has adopted Pulsar, primarily coming from so Iterable is a cross-channel marketing platform, and Iterable moved from many RabbitMQ clusters to as well as additional use cases that are in progress of being able to move to one single unified messaging system that helps reduce operating costs and improve reliability in additional use cases. It was just a sample of a few different customers. Adoption of Pulsar is happening globally across lots of different organizations of different sizes. So Flipkart, a large e-commerce organization out of India that is replacing Kafka with Pulsar. Obviously, Verizon Media, the original founders, continue to invest heavily into Pulsar. Lots of other organizations. Tencent is a very large user that's doing lots of different use cases on Pulsar. And so really happy to be working with many of these companies in the community and helping to adopt Pulsar, and really excited about the growth that we've seen there. So returning sort of at a high level, what are some of those benefits that we see? So some of those we've already talked on a little bit. We're going to dig a little bit deeper into here, such as scalability and unified messaging model. But one thing that's really critical in Pulsar's adoption story and what makes it very successful is its multi-tenancy model. So Pulsar is able to be a system that's designed to scale across your organization, not just in terms of traffic, but also different teams, different use cases that all can share infrastructure. And so it's designed for, it's centrally designed around having a multi-tenant infrastructure where you can have different teams that safely can share a cluster and share those resources. Scalability is one we sort of touched on, and once again, very obvious of needing to be able to handle large, massive amounts of throughput, gigabytes a second of throughput, and Pulsar is able to do that quite well. Another feature that is unique to Pulsar in being able to really provide, once again, this really unified infrastructure or simplified infrastructure is georeplication. This really makes Pulsar work well across maybe cross-cloud or hybrid cloud scenarios, where out of the box, Pulsar can span different geographic regions and use the built-in georeplication to do that. As mentioned, we talked about this unified messaging model of being able to do both messaging and streaming in one system, and that maps to a large set of use cases. So once again, work queues all the way to high throughput streaming and stream processing. And then finally, durability. Many users of Pulsar have adopted it for very business critical situations, things like billing systems in the case of Tencent, as well as other financial institutions that are relying on Pulsar's out of the box high level durability guarantees to make sure that the data is securely stored and that there's no message loss. So yeah, that's a bit of an overview of Pulsar, and we'll talk a little bit about StreamNative, who we are and how we participate in this ecosystem. So we have a team that spans the US, Europe, and Asia. And so we have a global presence of experts that know and have been working on Pulsar for a long time, as well as StreamNative Cloud, which provides a fully managed out-of-the-box solution for Pulsar. We'll talk more about these in a minute here. So first, the team. So StreamNative, once again, is founded by many of the original developers of Pulsar. So CJ and Matteo both worked on Pulsar initially within Yahoo. Matteo is the PMC chair of Pulsar, and CJ is another PMC member, with also Ja, our other co-founder, who is a Pulsar and BookKeeper PMC member. Once again, lots of experience with Pulsar, as well as more broader data challenges from companies like Splunk, Twitter, EMC, and Tencent. And we really are committed partners, right? Pulsar is very much a technology that we really see being able to help organizations use, when utilized well, really able to drive new capabilities. And we really focus on being partners, not to just provide software, but really to help provide end-to-end solutions, to provide experience support, to make sure that it's successful projects. Once again, we have not just among our co-founding team, but among the members of our organization, lots and lots of experience running some of the largest BookKeeper and Pulsar clusters in the world. And global support, once again, we span the US, Europe, and Asia, and are really able to provide great support to customers regardless of the geographic region they're in. And finally, we'll talk a little bit about what StreamNative sort of offers underpinned by Pulsar. So StreamNative Cloud is once again powered by Apache Pulsar, and it's a fully managed Pulsar instance that provides all those capabilities with messaging and streaming that can work both in multi and hybrid cloud strategies. So once again, it's cloud native, it's built for containers. And we also recently announced Flink SQL, which gives you the ability to have your Pulsar data be seamlessly processed with Flink SQL to kind of gain new insights, all fully managed by the StreamNative team. We also work with lots of partners to further expand and within the ecosystem, companies like Ververica, PingCap, Aerospike, and Scylla, of really providing a broad ecosystem of support there. Talking about the StreamNative solution, from a high level, once again, we've got Pulsar's ability to do lots of different use cases. So application messaging, data pipelines, as well as what we call this real-time contextual analytics, where we're taking historical data that we can store and process from Pulsar, and then merge that with real-time data for things like risk control, auditing dashboards, where we need that historical context, as well as more recent data to inform models. And then once again, we talked about Pulsar. It has a two-layer architecture where we separate from compute from storage. So we have core Pulsar, also on the processing side, Pulsar Functions, which is a lightweight framework for stream computing. And then for more complex stream processing tasks, using Apache Flink. And then at the storage layer, there's Apache BookKeeper. That's where what provides durability and high throughput, as well as the ability to move data into tiered storage like S3, GCS, et cetera, being able to give you infinite retention of your streams. And all of that is built on top. Kubernetes is our sort of common foundation across cloud providers, as well as like in on-prem situations. And StreamNative Cloud, both the cloud hosted, which is fully running in StreamNative's cloud accounts, or cloud managed, which runs in within your customer cloud account, being able to provide this whole solution. And really the goal of StreamNative Cloud is provide end-to-end streaming applications, once again, with Flink as well. And so you can kind of think of Pulsar as being a system for unified batch and stream storage. So it can do queuing, streaming, as well as offload data into tiered storage for accessibility for batch use cases, where you have Flink that can do unified batch and stream computing. So a computing engine that knows how to both leverage batch data and process that efficiently, large amounts in parallel, as well as then to seamlessly transition to streaming data. That all tied together with being able to seamlessly get data in and out of Pulsar, things like Pulsar sources and syncs for interacting with other systems, as well as being able to speak different protocols like Pulsar's protocol or Kafka Pulsar, KOP, as well. So a lot of ability to get data in and out, and then to process that data intelligently, all in sort of StreamNative Cloud. Yeah, so once again, a quick overview of StreamNative, who we are, what we do as an organization. And certainly if there's any interest there in learning more, let us know. But we'll move now to talking about the modern data needs and a bit more into why those capabilities of messaging and streaming, what they unlock for you organizationally, and what the new capabilities there that allow you to do new things faster and easier. So once again, this really is sort of is underpinned by this messaging and streaming capabilities. We'll talk more about why that is and how those differ, but most organizations have both of these needs. And by being able to unify those, we're able to simplify infrastructure architectures, as well as lower cost by having single set of infrastructure to handle both needs. And so once again, to talk about that a bit more concretely, many organizations, architectures end up sort of looking somewhat like this, where we think of application services. So these are the things that, powering our day-to-day business that our users are interacting with, et cetera, often composed of many different services. And these services have needs to communicate, pass messages. And this is very much a common need of asynchronous messaging, and messaging patterns have existed for a long, long time. Systems like RabbitMQ, once again, ActiveMQ, etc. These are things like fan out, work queues, whatnot. But as data volumes have grown and needs have grown around being able to do things like batch processing, real-time stream processing, the data ecosystem has grown. And as such, we often see many organizations that will have sort of a separate, sort of very separate regime group that is handling sort of data services. And they'll often have need of some of this messaging data. So that data may be replicated into like a streaming system. You know, maybe this is Kinesis or Kafka. That data then may need to be moved into long-term data warehouses for batch processing, as well as being used for sort of near-time stream processors, right? The sort of processing data as it comes in. And then, you know, we're doing something with that data, and then maybe perhaps actually like loading it back into other services for usage. So we sort of have, you know, data moving back and forth between these two different ecosystems in your organization, with you know, very different stacks and whatnot, and very different needs between these different groups. So once again, at a high level, when we talk about messaging, sort of more commonly used in the application domain, that's for things like work queues, fan out, where maybe we don't care about order, and maybe we're needing to do some work queues of splitting work. RabbitMQ, SQS, very common systems in this domain. Versus streaming workloads, where we really care about order, and we also care about potentially high throughput. Once again, Kafka, Kinesis, these are systems that more rely on streaming semantics historically. And so to kind of make this a bit more concrete, let's suppose a situation where we're doing an e-commerce system where you kind of have an order service, an inventory service, fulfillment service. They're passing data via RabbitMQ to fulfill some tasks. And then we have in our data services, maybe we're doing something like an inventory forecast, making sure that we have enough product. And that's being powered by you know, stream processing, as well as a batch processing system, sort of a Lambda architecture to get a view of what our inventory forecast is looking at near real time. But one of the things to note about this, right, is we have separate systems for both of these domains. We're using RabbitMQ here. We're using Kafka in the data services domain. So has to be that manual interchange of data. Additionally, there's somewhat of a tiering of data where we're moving data from our applications communicating into our streaming system, which then once again is where it may be stored for weeks, and then finally into our data warehouse where it's stored for long periods of time. But that tiering of data is maintained explicitly. It's something we have to do by cooking these different pieces together. Once again, these domains are quite different. They have different technology stacks, and the exchange of data is done through, you know, sort of heavyweight ETL processes or replication of data. Whereas with Pulsar, the real goal of its design is to give you a unified storage and transport of messages and streams with access to the underlying batch data. So here we have, you know, it's both being used for directly Pulsar's messaging capabilities are being used to connect applications, but those same messages, same data, same infrastructure can be used for both batch and stream computing jobs directly through its streaming capabilities, as well as being able to offload data where the native tiered storage allows us to offload data and then that to be read directly by like stream processors, batch systems, et cetera. So it allows us to have our application domains and data domains use a single system and a more of a shared tool set. And once again, so this is really the sort of the vision. The goal of Pulsar is to be able to simplify architectures by having one system that can provide more capabilities. It makes it easier to interchange and exchange data and really serve as a centralized system for a lot of that complexity that may be spread across multiple systems in other organizations with different technologies. Okay, so now let's talk a little about how we do that. You know, this is really interesting set of capabilities. We'll talk about what that really looks like in terms of usage. So first, to understand that, we'll talk a little about Pulsar's API design and how applications are able to have all this flexibility. So from a high level, the main API for dealing with Pulsar is the PubSub API. And so PubSub, I think a very common API pattern, a publisher is able to publish data, a subscriber is able to register interest in that data, and the broker sort of sits in the middle there helping to interchange that data between different systems. This is really great for microservices, event-driven architectures, a very commonly used pattern with systems like RabbitMQ, SQS that all sort of follow somewhat of a pub/sub model. But additionally, Pulsar has some additional capabilities in our reader and batch APIs. And these APIs are slightly lower level. They provide additional, more flexibility. For example, the ability to individually control your position in reading a stream of data, as well as our batch API that allows for you to read from the underlying storage directly. So you can read your data in bulk. That's really ideal for these stream processor applications, things like Flink, Spark, etc. Certainly that also can be used for microservice event-driven architecture as needed, but those APIs really provide an additional set of capabilities and flexibility. And then finally, all of these systems have a lot about interchange of data. And so the Pulsar IO / connectors framework, these connectors allow for connecting to things like databases, other messaging systems, et cetera, that all is managed by Pulsar and is quite easy to be able to get data in and out of Pulsar using this connectors framework. And so we talked a little bit about the APIs. Now we're going to talk a little bit about the logical components that make up the multi-tenancy model that really allow Pulsar to span organizations. So at the top level, we have what we call a Pulsar instance. And this can be many Pulsar clusters that sort of act as one. So this is how we allow you to have clusters that sit across different geographic regions that are doing replication among one another. That gives you unified management of all these things we're going to talk about. So tenants, namespaces, et cetera. And so it's a very easy way to think about, not just region by region, but really across your whole organization, one Pulsar instance composed of many Pulsar clusters. And multi-tenancy is really the key in making this work. So it helps provide structure and organization, also a mechanism of security and isolation. And once again, its design is so that you can have different departments or teams within an organization share a Pulsar cluster in a safe, reasonable way. And so once again, you have a Pulsar instance that can have one or more clusters. And this we're just going to show one cluster. And a cluster can have, or an instance can have many tenants. These tenants, once again, may align to different departments, data services, marketing, compliance, et cetera. And they provide a security boundary so that different organizations can each have their own tenant. And these tenants can actually also be spread or cross and isolated to different clusters. So maybe you have some clusters that some use cases that only need to be in one data center, one region, that can be done at the tenant level. And once again, it's the most basic unit of categorization ultimately for topics, the topics being where we're actually going to store and maintain data. And then underneath a tenant, there's namespaces. These namespaces are more aligned typically to applications or to specific use cases. So here we have, sort of our microservices, maybe multiple applications, ETL, risk assessment, et cetera. And this is what allows a tenant to sort of keep their data and team separate for the rest of the organization. So that once again allows for things like maybe a tenant or a namespace per team, or maybe a namespace per application. Namespaces also serve as a way to have sort of control over data in the so that we call policies. So this controls things like rate limits, whether data should have a schema or not, permissions, as well as the ability to use namespaces for like a boundary for being able to like isolate namespaces to different compute resources. And then underneath finally namespaces, now we have topics. And topics are where we're storing data. And so all topics exist uniquely within their namespace and tenant. So you don't have to worry about topic collision, et cetera. You can have different tenants, different namespaces that all can have the same name topic, and they're isolated or they're uniquely defined within those namespaces. And once again, these are the details we're typically dealing with directly in our application. So maybe this is customer authentication events, maybe this is demographics data, et cetera. And much like in other pub subsystems, there are these name channels that are for transmitting messages from producers to consumers. And you don't need to explicitly create topics in Pulsar. And so, once again, it's a pub sub model. The publisher sends data. It doesn't know about the subscribers or their status. All interactions go through Pulsar, and the subscriber receives data, never having to directly interact with the publisher. In Pulsar, we call that a producer and consumer. So pub sub model, and we call those a producer and consumer. And then finally, the topics are the mechanisms, these channels that are used for the producer and consumer to communicate over. Okay, so now with all of that conceptual understanding, let's look at this in the code. One of the things that I personally really like about Pulsar is that it's a very sophisticated system that offers a lot of capability, but the API is quite simple and easy to use. And once again, it's this unified API that supports a broad set of use cases. And one of the best ways to think about Pulsar is it's a flexible pub sub API that's built on top of sort of a modern distributed scale-out log system. So you get a higher level API, but all the capabilities of scale-out distributed systems, and still get to leverage all those capabilities. Once again, it gives you this infinite segmented streams with multiple levels of API access. So there, just for context, there's official language bindings for Java, Go, Python, C++, C#, and Node.js, as well as a number of community bindings in progress like Rust, Erlang, Haskell, and many bindings built on top of the C++ bindings using FFI. And once again, this client API, it encapsulates all of the client-server communication and provides this real simple, intuitive API for use in applications. So from a code perspective, all data is sent through a producer, the producer interface, and it can send data asynchronously or asynchronously. And when you use asynchronous sends, that allows us for Pulsar to take on a role of doing some intelligent things there, like buffering your data into batches so that you can get higher throughput, higher performance. As well, it's important to know that all of the Pulsar APIs have a built-in notion of schema. So you don't have to worry about, you can use Pulsar's APIs for deserializing, serializing your data and ensuring that you're getting easy to read and easy to understand data. And once again, as I mentioned, one of the things, my favorite features is all this complexity in a somewhat simple to use API. Here we can see here, we're creating a Pulsar client that uses just this service URL. We then are able to create a producer that writes to a topic. Notice that this is, here we're using a default schema of string, but this can also be something like a data type, a class, etc. And then we create a message with a key and a value. We send that message, and here we're also closing that and producing that. As mentioned, we can also use a synchronous send, or sorry, an asynchronous send, where we're not, this is going to allow for things like batching, and it's can be very useful in higher throughput situations. Likewise, the consumer API is the main mechanism you're going to use for receiving data. And it has a polling model, but actually there's a lot of prefetch and other things happening internally with Pulsar to make that be very fast. Once again, aware of the schema. And by default, it's going to start at the most recent data arriving. And so as we look at this, it's very similar. We use that same Pulsar client object to create a client instance. We create a consumer. Once again, this is schema aware. Here we're just using string, but can be more complex. We have that same topic name and then also a subscription name. This is important, as this is how we sort of can have a single topic can have multiple independent subscriptions. Let's say you can do things like fan out, whereas with the work queue, we would want to share that subscription name. And then finally, we call receive, we handle it, we receive a message, we handle that message, and then we can acknowledge that message. There's also an asynchronous receive, but once again, there is sort of prefetch and what going on there, so that consumer receive is a very reasonable API to use. And as we mentioned about here, there's a subscription. And the subscriptions, this is really the way in which Pulsar is able to do, have all this flexibility of across different use cases. And so a consumer sort of binds to a topic, registers their interest via a subscription. And it's important to note, once again, that a topic can have multiple attached subscriptions. So you can have multiple different ways you're consuming that data and multiple different applications. And internally, a subscription consists of a cursor. And this cursor is how we sort of track the position in our topics. And once again, so here is this different subscription modes. these provide different semantics that are very useful for different needs. So an exclusive and failover, these give you guaranteed order, but you can only have a single active consumer. So in the case of an exclusive, if another consumer tries to connect, it's going to get an error message. Whereas the failover, that consumer can connect, it will not receive any data, and it's sort of seen as a hot standby. If you're coming from a Kafka ecosystem, this failover consumer is semantically equivalent to a Kafka consumer group. We'll do all that same distribution of data, et cetera. But Pulsar, goes beyond just those more sort of streaming use cases with a shared subscription, which is really ideal for work queues. So you lose out in order of that, or on the guarantees around order. Messages will come in not strictly ordered, but you gain the ability to have multiple active consumers. So you can use that once again, very much like a work queue. And finally, there's key shared, which is a very unique capability that is very useful in certain streaming situations where now you can have multiple active consumers and have order for a given key. So if you're maybe coming once again from a Kafka ecosystem or Kinesis, where you can only have one consumer per partition or shard, with Pulsar, you can have multiple consumers, still get order guarantees, but over a given key. And so once again, some of these are very useful for streaming use cases, key shared, failover, very heavily used in streaming, versus shared exclusive, very much sort of more messaging use cases with work queues and sort of like a fan out, like a message bus. And finally, we talked a little bit about that reader API. This API allows the consumer to read messages and specifically control its offsets, so where it's going to read from. So that can be the earliest message, the latest message, or any message in between. And each time that reader connects to the topic, it's going to specify where it should be reading from. So with consumer, once again, Pulsar is managing that cursor for you. You start at whatever was the most recent position, the recent unapp message. Whereas with the reader, it can be any message in between. The state of how to control that is sort of entirely up to the reader. Once again, that's super useful in if you're writing like an integration to a streaming system like Flink or Spark, but also can be really useful in certain applications where you're just going to periodically come and reread some data and pick it up from Pulsar. Okay. So now we'll talk, we've kind of talked about the API design, multi-tenancy. Now we'll dig into the architecture a bit deeper about how Pulsar is able to do all these different things and provide, and is able to, once again, have scalability, durability, high performance, no single point, fault tolerance, excuse me. So Pulsar, well, as we talk about this architecture, it's important to note that a lot of these provide, a lot of unique advantages. A lot of the things that Pulsar is able to do is directly related to its architecture. And a lot of thought and design went into making sure that this architecture can provide all these capabilities, is such to provide all these capabilities. And so that allows for, once again, things like easy scale out, automatic rebalancing. So Pulsar is a system that, from an operational perspective, doesn't require any sort of manual operation as you scale out. It automatically rebalances, as well as isolation. Multi-tenancy is directly due to Pulsar sort of unified management from a metadata perspective. The segment-based storage, which we'll talk about, this is how Pulsar is able to have tiered storage out of the box that allows for offloading of data to things like S3, while still being able to get all the capabilities of, there's no change to the end user, being able to read that data back out, which makes infinite retention cost effective. And then finally, Pulsar SQL and being able to do batch reads, that really is, once again, powered by Pulsar search segmented storage, and be able to then do more interesting things with data, understand your historical data that's stored in Pulsar. So once again, a Pulsar instance can be composed of many Pulsar clusters that are replicating data between each other. But we're going to focus first today on an individual Pulsar cluster, what that looks like. And so Pulsar cluster is composed of three main components. So we have the Pulsar brokers themselves. These are the what clients are interacting with, all the clients connect to, but it's a stateless system. So it has caches for performance, but it is actually not storing the messages. Instead, messages are stored in Apache BookKeeper. Apache BookKeeper can be thought of as a distributed write-ahead log. So it's a system for very durably storing data that is ideal for sequential writes and reads. And then both BookKeeper and Pulsar, they share ZooKeeper as a common dependency, which is used for service discovery and metadata needs. And so together, these three components kind of form a Pulsar cluster, and deployments will always have at least one of these components, but can be noted that there's more. These can actually be mixed and match. You can have multiple Pulsar clusters that share a ZooKeeper, or multiple different groups of Pulsar brokers that share a ZooKeeper, as well as that can share BookKeeper. Likewise, there's some flexibility here that really can allow for very large Pulsar clusters. Once again, this architecture provides high availability, fault tolerance, and easy scale out. So cloud native, once again, we'll talk about how that looks of add more capacity, running across a variety of different hardware running in the cloud that seamlessly scale out. And once again, designed for failure, automatic recovery, and without scaling out, not having to do any sort of automatic rebound or manual rebalancing. It's all done automatically, and separating out your compute and storage. Okay, so we've talked about producers, consumers, topics. A topic can be composed of many topic partitions. So this is how Pulsar is able to scale out have one topic that can span many brokers. And each one of these topics is composed of a sequence of segments. And these segments, a sequence of segments make up a topic or a topic partition. And when a producer is writing to producers are only ever writing to the most recent open segment. And then older segments, these periodically will close, and then this data becomes immutable. It doesn't change. It's immutable data. We'll talk about why that's important in a bit here. And once again, the sequence of these is together is sort of event stream, is a topic or a topic partition. Oh, it should be noted, while a producer will only be producing to the most recent segment, consumer can be reading from older segments, catch up and read historical data. Okay. So here we have kind of a representation of a Pulsar cluster. We have our brokers, which once again, these are stateless components, and they serve topics or topic partitions. You can think of them interchangeably in Pulsar. So if a producer wants to write to a given topic and a consumer wants to consume from that, they're actually directly connecting to that underlying broker. And bookies, their job is to store segments. So from here, where we talked about these segments opening and closing, those segments actually live on bookies. And so we'll talk about now, with that in mind, how Pulsar is able to scale. So first, let's suppose that our brokers, they're getting busy. We need to add more brokers. So we add an additional broker. Because this component is stateless, the topic can easily, Pulsar will notice that there's new capacity and can then easily be reassigned to shift load around the cluster. And so now producers and consumers who wanted to interact with topic 4, they shift their connections to broker 3. They're able to resume and pick up. The Pulsar clients take care of all that complexity. So it's abstracted away from end users and allows for Pulsar to seamlessly scale out and add additional capacity. Likewise, if a broker crashes, that topic can immediately be reassigned to another broker. So we have high availability. There's no single point of failure here. And we reassign that topic to a new broker. And once again, the producers and consumers will reconnect to that new topic and resume with little to no interruption. Likewise, we can scale out of the bookie tier. So because we're periodically, and this happens in the orders of in busy clusters every couple of minutes, or on the order of hours for smaller clusters, less busy clusters, new segments are always being opened. And each time we open a new segment, we actually choose a new group of bookies. So as soon as a new bookie is added, it's immediately going to start being used for write capacity. And that allows you to, once again, not have to have any rebalancing. You're maybe able to leverage that new compute as you add it to your cluster. Likewise, if you have a bookie crash, when a bookie crashes, the Pulsar brokers are going to notice, hey, I'm not able to write to this bookie anymore. They're going to choose a new set of bookies to continue to write to so that we don't have any impact. Losing a bookie does not impact our rights. And we have redundancy of writing data to multiple bookies so that we can continue to serve older reads from one of the remaining bookies. And then finally, we talked about how these segments periodically close. Because we have this segmented architecture, it's very reasonable to take these segments, move them to a different set of storage. So now we're minimizing the amount of storage we have to manage on disks, and can instead leverage cost-effective cloud storage for longer retentions. And once again, the clients don't have to change anything. The brokers will now seamlessly read from S3, GCS, et cetera, and continue to serve reads and from those places. Once again, that's how we do infinite stream storage. And finally, once again, so all these segments here that are in gray can be offloaded into S3. So we're only having to keep some of our more recent data that we're actively writing to. Once again, with BookKeeper, that is not, it's not a direct dependency that clients interact with. The producer and consumers interact with Pulsar, and then Pulsar uses BookKeeper as a dependency. This allows Pulsar to be scaled independently, and BookKeeper once again can be scaled independently, with Pulsar being stateless and the Pulsar broker having some state. And this this same tiered architecture also provides for a lot of flexibility. So if you have different use cases, you can really tailor a Pulsar cluster for your needs. So if you have a high amount of what we call tailing reads, so a lot of connections to get their own copy of a message, you can add more brokers. You don't need to worry about scaling your BookKeeper tier as much, because that's primarily going to be served out of the BookKeeper caches. Whereas if you have lots of historical data, maybe you have periodic processes that read historical data, you may not need as much on the broker. You're going to have more bookies with more memory for better read caching. Versus if you just have write throughput, once again, you don't need as much with BookKeeper. You're going to need more bookies with fast disk and less memory. And finally, one unique aspect of Pulsar is it has what we call the Pulsar proxy. This allows for you to simplify networking, so you can have a single endpoint in front of your Pulsar cluster that now clients interact with, and allows the proxy to dynamically discover and connect to your brokers, which can be useful in some environments where it's difficult to sort of have a full network peering, and instead useful to have a single TCP, HTTP endpoint. And finally, we'll talking about here about the architecture is the georeplication, where we can have multiple data centers that are tied together. And this replication is done asynchronously. And it should be noted, this georeplication is used quite heavily in production in a lot of large organizations. Okay, so that's an overview of, once again, Pulsar's architecture. There's a lot of interesting details there, but we'll finish up the day by talking a little bit about the Pulsar ecosystem. Once again, messaging systems particularly, and they're connected with lots of things, really need to have a strong ecosystem of being able to interact and interop with other systems. So some of that happens via our functions and connectors framework. So functions, once again, they're lightweight stream processing. We'll talk about what that means in a minute. But there's also connectors that allows you to connect to things like databases, files, cloud services, et cetera. We also talked about protocol handlers. So protocol handlers are really interesting. They're they allow Pulsar to handle additional protocols that are running in the broker. So this isn't some sort of proxy API that you're putting in front that's doing a translation. It's actually that protocol being implemented on top of Pulsar internals that make use of Pulsar's flexible ability to handle lots of different use cases in one system, once again, running inside the broker. So we have AOP, AMQP, KOP, and MQTT. So this allows you to have a protocol handler that allows Pulsar to seamlessly do speak Kafka, for example, as well as continuing to use the Pulsar protocol. Finally, processing engines, Flink, Spark, as well as things like Pulsar SQL, which is built on top of Trino, as well as offloaders that allow, once again, that data to be moved into tiered storage, S3, GCP, et cetera. So talking a bit more about Pulsar Functions, it's a simple API to receive, process, and send a message. So it really allows developers to focus on the business logic. They don't need to create the boilerplate of producers and consumers. Additionally, that code gets uploaded into Pulsar and managed for developers. They don't need to deploy a separate application. They can just write a function and produce data. This relates to Pulsar IO. It's actually Pulsar IO and functions share the same common framework. So this is the same mechanism. You can create a source, for example, that runs inside your Pulsar cluster, connecting to other services and pulls data in a sort of fully managed way into your Pulsar cluster. One of this really, processing engines like Flink and Spark is something we're very actively working on. As I mentioned, a Flink unified batch and streaming connector is in progress. So this is the ability to read batch data and then seamlessly transition to streaming data in sort of one Flink job. Similar capabilities will come to Spark at some point in the future, but we're currently focused on Flink. And once again, Pulsar SQL allows you to, it's basically built on top of Trino that allows you to query data directly from BookKeeper and tiered storage. And as we mentioned, StreamNative is working closely to integrate with Flink, which really is, best of breed stream processor able to do high throughput, near real-time stream processing. That's really ideal for ambitious stream processing compared to Pulsar's lightweight stream processing, Pulsar Functions lightweight stream processing. So always a lot of questions around this, where really you can think of Pulsar Functions as a very simple API for doing things like routing, simple transformations, whereas Flink is a framework that can do lots of redistribution of data, ordering, guarantees, state, etc. And once again, returning to this diagram, Flink is really where we look to offer a unified batch and streaming compute that is part of StreamNative Cloud that complements Pulsar's unified batch and stream storage. And then finally, to talk once again a little bit about this batch access. So this allows for things like Pulsar SQL built on top of Trino to directly read from BookKeeper as well as tiered storage, and then to, in parallel, answer questions about your streaming historical data. So once again, a very unique capability unlocked by Pulsar's architecture. And then finally, if this training was really interesting to you, if you want to get to learn more, we have an upcoming training calendar where we have our developer and operations training for those looking to learn more about Pulsar. And otherwise, you all have a wonderful rest of your day or evening, wherever you may be. And we'll hope to see you around in the Pulsar community. And please always feel to reach out to StreamNative. We can help you with anything else in sort of your Pulsar adoption. Thanks so much.